Okay. So so yeah, as I was saying, in today's meeting, like the point is not to like show you how to integrate in higher dimensions because um because the notions that I'll give a couple examples of two dimensions. We'll introduce a important um computation tool and even proof tool called change of variables, right? Which will allow us to, instead of integrating over like weird surfaces, we can integrate over nicer surfaces. But then if you remember from like U substitution from single variable calculus, you you your your integral changes by a factor of the derivative. Um, so that's one of the things. Another thing is I have not really intended for this meeting to really be comprehensive, like it's more to give you an idea of what there is in, classical multivariable calculus. Um, rather than really go into the nitty-gritty of each detail and, stuff like that. Um, if you want to learn the computation of whatever we're going to talk about today, uh, Griffith's E&M book is, I don't know, it's a good place to learn. That's where I learned all my multivariable integration.
What is the name again?
Um, like I don't know, it's Griffith, like E&M by Griffiths.
Okay.
It's the standard like E&M book. I think 250 uses it, no?
Oh, I'm having that next semester, so probably yeah.
Okay, okay, yeah. So it's the standard E&M book. It's a standard E&M book, like 250, 350, 450, all use Griffiths. Chapter one is where he teaches like all of vector calc. So if you want to like learn the computations and stuff, you can um look at that. Stewart is another good resource. I forget the title. I think it's called Early Transcendentals of Calculus or something like that. Um, so yeah, today is just to, show you that okay, these are the things you can do in multivariable integration, like classical multivariable integration. Um, but it turns out that you don't actually need to know any of these things to do integration on manifolds. All you really need is the change of variables, like the change of variable theorem, and the and Fubini's theorem to really get the computations down. Because as we will see, we would really hope that, like classical multivariable calculus is just a special case of, differential geometry, or like the theory of manifolds that as we'll develop, right? Um, so yeah, so this meeting is again, like I said, is just a lot of the formulas are going to be extremely unjustified. Um, I don't think, at least for now, it is really needed. Like a lot of the formulas are needed to be justified, because in their current presentation, they will look extremely unnatural, and that's because they are. They're very specific to the case of three dimensions, right? Um, and because of that, I mean, it will look very unnatural. Um, so that's one of the reasons I'm not really gonna go into the, details about um, everything. Another reason is you don't really need to know how to do it. Um, and so yeah, so today we're just gonna mention the main theorems, and this is gonna be more of like a motivational, um, like this is gonna be like what are we actually generalizing? You know, because we can generalize things for the sake of generalizing things, because why not? But in this case, there's actually things that we're generalizing. Um, so yeah. Another thing of note is that I was initially going to talk about ODEs and PDEs as well, um, like in the prerequisites. Um, but then I realized that like everything we really need for the ODEs and PDE theory that we're going to use um, is in problem sheet 2 and 3. Like there's only a couple things. Like for example, with ODEs, we need like Picard-Lindelof. I've outlined the proof step by step in problem sheet 2. Picard-Lindelof like just tells you when solutions exist to ODEs and like if they're unique. Um, another thing we'll need is the exponential, like the matrix exponential, which I've outlined in problem set 3. In terms of PDEs, you just need to know what the Laplacian is, and how we'll define it. I'll define it today because I remember I forgot to actually do it in when we talked about the derivative. So I'll define it today when we talk about the you know multivariable integral theorems. Um, so yeah, all and I've given a couple questions about like conservation of energy, you know, stuff like that in problem set 3. So yeah, we don't really need to worry about that too much. Final point of note is that next week's meeting is going to be so not next week. I get the next meeting is going to be extremely how do I say this? It's going to be again, it's going to be one of these like motivational type of meetings. It's um I sort of expect that a lot of the content will not really make sense. At least in the first pass, you know. Um, and that's to be expected actually because this is we're going to talk about like category theory. Um, and category theory is I don't know, by sometimes I feel like it's by design, but it's extremely it took me some time to get used to the ideas of category theory, and that's mainly because I'd never seen um, things presented in category theory before. So in problem set 1, we discussed like the universal property of tensor products, and turns out that this is sort of like a more general idea in mathematics. So we'll see that like like the Cartesian product, for example, is has a certain universal property. So does the product topology. So does the disjoint union of sets, stuff like that. So we'll see that like even though the ideas in category theory are extremely useful, the notion of a category and the notion of category theory is extremely, extremely, extremely um, you know, theoretical by nature. Because the idea is the category theory can be summarized by saying that you're studying the structure of math. Okay. You're not really studying a specific object. Okay. But you're studying how this object relates to other objects in its, um, class or whatever. So yeah, again, next week's meeting is almost by design going to be extremely hard to follow. But again, I just wanted to like introduce the ideas of category theory rather than, like I just wanted to make sure you know what's out there and why people study the things that they do. And we'll see later on as well that a lot of the ideas will come up again and again and again and again. So, for example, we'll see the notion of something called a functor come up in differential geometry when we talk about tangent vectors and stuff like that. Okay. Um, so in hindsight, category theory will be something useful to study, but it'll feel extremely unmotivated in the beginning. Yeah. So I know this is usually the order, like the reverse of the order people present category theory, and like it's very good to, have a strong baseline of knowledge and then jump into category theory. But um, I don't know. I feel like if I present it before and then we see these ideas, maybe that might, spark a eureka moment. Um, you know, and then you can look out for when certain like objects are actually universal in a sense that we'll define. Okay, so with all of this out of the way, let's begin with sort of a generalization of U substitution. Okay. So if you remember from U substitution, the idea was to reverse chain rule in a certain sense, right? Um,
Mm.
because if you had something of the form the integral of f, so U substitution. So if you have the integral of f of g of u or g of x, g prime of x, x. This is the same thing as the integral of f of u du, right? Where u is g of x. So in some sense, we went from an integral that looked very complicated to an integral that's slightly easier to deal with. Another way to see this is I changed the domain of my integration, right? Instead of integrating on a certain square, I have integrated over another square, right? And this is the notion that we'll generalize. So the idea, I mean, the question that motivates all of this is let's consider the integral over the ball of radius, I don't know, r of x squared y squared. Okay, this. Okay. Now, how do we integrate this? Right? How to integrate this? Now, we've only really like Fubini's theorem allows us to integrate over a rectangle, right? Um, where we break it up into two integrals over each of the sides. But a ball isn't really a rectangle. So the question now becomes, can I deform the ball to make it into a rectangle? Right? Um, and the answer is almost, right? You can deform it continuously to give you a rectangle. You can't do it smoothly. Right? Also, when I say ball, I mean like even the surface of the ball. Um, so, um, so can we deform B0R into a rectangle? I'll put the closure because why not? And the answer is almost. We can do it continuously, but not smoothly. And the way you want to think about why that is because I mean, like a rectangle has corners, it has sharp corners, but a ball is like very smooth, right? So in some sense, like sure, I can like push out the edges, but that'll make a singularity at some points, right? And uh, so we can do it continuously, but not smoothly. Um, but remember, the singularities here are measure zero. So in terms of the integral, it doesn't matter. Okay. So the singularities are measure zero. So they don't really matter for the integral. Because remember, the integrals over measure zero sets is just zero. So that has no effect on the integral. Okay, so armed with this, what we're gonna do now is, say we have two regions, and we have a diffeomorphism of the regions. Do you know what a diffeomorphism is? Okay, so let me define that. So, um, how do I want to define this? So I think for the change of variables, it suffices if the diffeomorphism is C1. Um, but in what we want to do, we'll restrict ourselves to smooth functions, like infinitely differentiable functions. Um, so I'll just I'll just define a diffeomorphism to be a smooth map with smooth inverse. So f from u to v is called just to set up the way I'm gonna do this. Let's call this f from v to u is called a diffeomorphism if um if f is c infinity. Have you seen this notation before?
Yes.
Okay. And bijective so that f inverse is also c infinity. Yeah, very simple. Okay, so now one caveat that we will do when we do integration is that we'll allow diffeomorphisms to fail up to measure zero sets. Okay, so for what we will do, we will do we allow f to be non-diffeomorphic, diffeomorphic up to a set of measure zero. Okay, what do I mean by this? So let's look at polar coordinates. Okay,
It's okay.
yeah, no worries. Let's look at polar coordinates. Okay, so in polar coordinates look something like x equals r cosine theta, y equals r sine theta, right? Where r comes from like this and theta comes from this, you know? Um, but you see the issue is that if theta equals pi over 2, it's the same thing as if theta was equal to 0. Okay. Also, another issue is that this isn't well defined at the origin because theta could be anything because r is 0. Okay. So now you see, so already when we're talking about circles, it's already bad enough to like try to find, diffeomorphisms that are actually diffeomorphisms. But if we think about it, the only place this thing fails is the ray along the x-axis that starts at 0 and goes to the positive x-axis. Okay. So this fails only on um how do I want to write this? So I guess I'll do x bigger than or equal to 0 times r. No. Okay. So it only fails on this line. Okay. But a line is measure 0 in a plane, right? A line has no measure. So we allow these things. Okay. Because otherwise it would be extremely inconvenient to try to find proper diffeomorphisms. Okay. Um, so yeah, okay. This example already shows us that okay, we now have the ball. We can look at it as a rectangle in polar coordinates. Okay. So a ball is a rectangle in polar coordinates. And how do I see this? Okay. So say I have the ball of radius capital R. Uh, we have xy in this ball when so xy is in this ball if and only if x squared plus y squared is less than or equal to r squared. Okay, r squared, right? But this is the equation of a circle. I mean, like they're concentric circles, right? So, so we have that x equals r cosine theta, y equals r sine theta, where um, r comes from 0 to capital R, um, and theta comes from 0 to 2 pi. Again, we allow like measure zero sets, whatever. So okay, so we have this ball, right? And um we have this ball, but now this is in the xy plane. But now if we move to the r theta plane, this is nothing but this rectangle, right? So this is the r axis, this is the theta axis, this is 0, this is 2 pi, this is capital R, right? So okay, so we can convert balls into, rectangles. How does this help us with integration? So this helps us in the following way. So we have a theorem called the change of variables. Change of variables. So if you have, for example, if um, we have a function f from u into r extended, um, and everything here is, subsets of Rn, um, and we compute the integral over u of f with the Lebesgue measure, okay? And we have a diffeomorphism up to measure 0. Diffeomorphism up to measure 0 sets from of f from V, some other subset of Rn, into U, okay? Then the integral of U, sorry, the integral of f over U, okay, um, is equal to the integral of f composed with capital F times the determinant, sorry, times the absolute value of the determinant of the diffeomorphism times d and b. Okay. So this is basically the exact same thing as we had up here, you know. Um, if you compare it, it's basically exactly the same. So u here is your capital F. So you have f of u times g prime, and then here you have the determinant of the derivative. Um, yeah. Okay. So one thing to notice here is that um in this case you could allow g prime to be negative. Okay, so you have some sort of orientation here. Okay. But when we come down here, the orientation sort of vanishes, right? Because you have absolute values. We will see later on that this is also sort of unnatural. Um, but I'm debating if so this thing is called a density. We may or may not see that, but that's to allow if your surface is non-orientable. Um, I don't know if I want to talk about non-orientable surfaces though, because a lot of the physics is not too. There's a lot of things you can't do on non-orientable surfaces. So if your surface is orientable, these absolute values, as we will see, will vanish. Okay, they won't be there. But yeah, we'll see that like I don't know, a couple months, like a couple months from now, probably. Um, but okay, for now, we'll just take this as a given. The proof of this is extremely involved, as we talked about last time. Um, if you want, Moncrief's analysis on manifolds has a chapter dedicated to the proof of the change of variables. Like the whole chapter is nothing but the proof of the change of variables. And there are a couple chapters before that that build up the required math to be able to prove that. Yeah. Are there any questions? Okay. Um, what we will require one of the things, like we will use one of the tools um, that he develops in that chapter to talk about various other things, and that's called the partition of unity, or not the a partition of unity. So okay, partition. So definition. So suppose we have a topological manifold. Do you remember the definition of a topological manifold?
I have to go back and check, but
Okay, so the idea is that you're at each point you look like Euclidean space. And globally, you can separate points with open sets, um, and you have a countable basis. Um, yeah, so if you have a topological manifold, um, and you have U alpha is an open cover. Remember, an open cover is just a collection of open sets whose union contains your manifold. So it's an open cover of X. Okay. Then this open cover has to satisfy like certain conditions. Um, I don't think that the conditions are, I mean, okay, the conditions are important, but there are some conditions that we'll now list. So then there is a collection. There is a collection. Um, so there's a collection of maps called rho alpha from U alpha into R of continuous maps. Continuous maps such that one, um, for each x in x, we have that rho. So rho is between 0 and 1. Okay. Two, for each x, there is um, a there's only a finite number of open sets, U alpha such that X is in U alpha. So this is the condition on X. Sorry, this is the condition on the open set. Um, so I mean, you can reword the theorem, the definition a little bit, to say that if you have an open cover that satisfies this condition. Okay, let me actually do that because okay, so X is an open cover. What? Um, such that for each X in X, there's a finite number. Okay. And then there is a collection such that these things. Um, this is a definition slash theorem. Okay. So it's both a definition and a theorem. It if you can find such an open cover, then these partitions of unity exist. So that's the theorem aspect. And then we define a partition of unity to be precisely this collection of sets. Okay. And two, for all x in x, we have that the sum over alpha of rho alpha at x equals 1. Um, and 3 of each rho alpha vanishes uh, outside an open set containing containing u alpha. Okay. So the idea is that you can use partitions. Oh yeah, and then u alpha rho alpha is called a partition of unity. So why is this useful when it comes to integration? Um, so the idea with partitions of unity are that if you're integrating over a certain region, right, you can break that region up into pieces that might overlap. Okay. Then what you can do is you can integrate on each of the individual like pieces because that might be easier. And then you can glue them all together. You can piece them all together using a partition of unity. Okay. Um, so a partition of unity basically breaks down the function one. And then so that if you're adding a bunch of things and they overlap, right? The partition of unity scales the overlap just correctly to get the proper integral. Okay. So we'll actually use partitions of unity later on as well when we want to take a bunch of local data. So say we know something exists locally, right? And then we'll use a partition of unity to piece all of that together to get something on a global level. Okay. Are there any questions regarding what a partition of unity is? Okay. So yeah, partitions of unity will be are used in the proof of the change of variable. Um, okay. So let's see how we can use the change of variable to now integrate this guy. Okay. So let's now integrate this thing. Okay. Excuse me. Yeah. So now we know okay, step one is to now find a diffeomorphism up to a set of measure zero of this set to a rectangle. But we already did that, right? That diffeomorphism was given by a by the like polar coordinates. Um, given by r theta maps to r cosine theta r sine theta. Okay. Now we find the derivative. So that's step one. Step one. Step one. Find diffeo from the sorry, from a simpler space. Simpler. Is that how you spell simpler? Simpler space into our disk. And as we saw, this is given by the polar coordinates, you know. Okay. Step two is now to find the derivative. Find df. But df is nothing but cosine theta, sine theta, negative r sine theta, r cosine theta. Step three is to find the determinant, like the absolute value of the determinant. This is the absolute value of r cosine squared theta plus r sine squared theta, which is nothing but r. Okay. Step four is that the integral over this disk of x squared plus y squared Now we want to write this in terms of the integral of like over this rectangle. And now we can see very clearly that x squared plus y squared is nothing but r squared in polar coordinates, right? So this is r squared, and then you multiply by r, and then the the measure, which is dr d theta. And now you have the iterated integral, right? As we had many times, r cubed d theta dr, which is nothing but 2 pi times the over times the integral. Now that you've used Fubini's theorem, sorry, this should be r, this should be 2 pi. So now you can just use Fubini's theorem along with the fundamental theorem of calculus um, to get um, pi r to the 4 over 2. This is just the fundamental theorem of calculus. Okay. Does this make sense? Does change a variable make sense?
Yeah.
Yeah. So the idea is you just, sorry?
No, yeah, I think it does make sense.
Okay.
It's just
One thing to notice is that we took an integral, right, from one domain, and in some sense we pulled the integral back. What do I mean by this? We, if you saw, our diffeomorphism was into the space that we're integrating over. And so we pulled it back to this rectangle. Does that make sense? We pulled it back. Okay. If you've seen problem set one, the question regarding tensor products, we saw also that there was a pullback function on tensors. Okay? So there's a way to pull back. So in some sense, we can already see that integrals and tensors are, should be related in some sense. Because we motivated integration in multiple dimensions using the determinant, right? Which is already like a rank n tensor, alternating tensor. And now we can see that, okay, we're pulling things back. And the pullbacks are very, very reminiscent of, tensor-like things. We'll see later on that this thing we integrated is called a differential form, which to each point in our manifold assigns a tensor. Okay. Um, but again, this is just something you should keep in mind for now. Um, does this pullback thing make sense? Do you see why it's called pulling back the integral? Yeah, because you're going from one space and instead of going forward, you're using this function to come backward. Yeah. Okay. We can also compute the area of a circle. So we can compute area of circle. This I'll leave as an exercise because I've already taken a lot of time. Try to see how you can use this to show how you can do change a variable to get this. Okay. If you check the lecture notes, I also derive the area of an ellipse. Okay, with semi-major and semi-minor axes given by um, a certain thing. Okay. Um, so I mean, okay, I won't write that down, but you can see that. Okay. One of the most important applications of this, right, um, is that we can compute integrals in one dimension by just bumping up the dimension, integrating in a higher dimension, which, seems a little counterintuitive because you would imagine that integrals in higher dimensions would be, harder. I mean, in some sense they are, um, but sometimes they make life easier as well. So one of the most important places you might see this is something called the Gaussian integral. So consider the Gaussian integral. Gaussian integral. And this is the integral from negative infinity to infinity of e to the minus x squared dx. Yeah. Again, so this is actually outlined in two places. So if you look at problem sheet 3, I've outlined the proof that this integral is actually equal to the square root of pi, but it's also in the lecture notes. Um, I will skip over it for now because again, I spent too much time on the introduction. Um, but I've done step by step of the derivation. So check. So if you want to try it on your own, if you want to try on your own, check problem sheet 3. If not, check meeting plan. Okay. It's outlined. I mean, I've done the solution. Okay. There's nothing special about two dimensions, as you saw. We did change a variable in arbitrary dimensions, Rn. You can also do spherical coordinates. Again, spherical coordinates are not diffeomorphisms onto the, image. It's just up to a set of measure zero that they are. So, so in R3, we have spherical coordinates. Okay, one thing to keep in mind that spherical coordinates, physicists and mathematicians use different conventions for spherical coordinates. The convention I use is the mathematician's convention. Physicists just have the theta angle and the phi angle swapped. It makes no difference on the evaluation of integrals whatsoever because they're just names of variables. But yeah, I just wanted to mention that. But in spherical coordinates, you have x equals r cosine phi sine theta, y equals r sine phi sine theta, and z equals r cosine theta. Okay. You can then check that df is given by r squared sine theta. The computation is not hard, it is just annoying. Um, and then you can use this to compute the sort of the volume of a sphere. So we can compute a volume of sphere by integrating over the ball of radius 1 or radius r if you want to be more specific times 1 times this. And then you can write this as an iterated integral um, as follows: r squared sine theta d theta d phi dr. And then if you do the iterated integral, you just get 4 over 3 pi r cubed. Okay. Um, okay, I forgot to mention um, the domain. So r comes from 0 to infinity. Phi comes from 0 to 2 pi, and then theta comes from 0 to pi, 0 to pi. Okay. Um, if you haven't seen this before, don't worry. You will see it in you'll see it in E&M courses. You'll see it in you'll see it everywhere in physics. Um, there's also cylindrical coordinates that are extremely used, but um, they're just polar coordinates bumped up a dimension. That's it. Um, Also, one thing to notice is that spherical coordinates and polar coordinates if you look carefully, the R term, sorry, the last component looks very similar. Okay. It's just R times either sine or cosine. You can swap these, it doesn't actually matter too much. Um, but you can actually build up the higher dimensional, like spherical coordinates by, you know, starting with, okay, say you want, so this is just an aside on higher dimensional spherical coordinates. So what you can do is you can start with, say you have like n dimensions, then your coordinates would be r, theta 1, theta 2, all the way up to theta n minus 1, where, r would come from 0 to infinity, theta I would come from 0 to 2 pi, um, for um, I not equal to n minus 1, and then the last component would come from 0 to pi. Um, and then you can write them as, let me just make sure I have this right. Excuse me. Sorry, one second. You have x1 is given by r cosine theta 1. xp is given by r cosine theta p times from m equals 1 to n minus 1 sine of theta m. And then the last coordinate um, is given by r times the product of um, the sines of all the angles. Okay, so it's sort of the same generalization where you just keep, if you write it out, you'll see that it's exactly what we talked about. Okay. Um, I guess here, just to make things like more, you know, the same, we can just do that. Are there any questions? Okay. Um, okay. Um, okay. So I mean that's integration of, over volumes. Um, but we we um we introduced integration in multiple dimensions by looking at line integrals, right? We looked at how much work does a force do on a body. Um, so let's go back to, where we started from, and let's, generalize those ideas. So to do those, what we're going to do is we're going to define the following operators on functions. Okay. So, oh, oops. Define. So one, if u is a function from Rn to R, okay, then the gradient of u is just the derivative of u. Okay. Um, we will use this and this interchangeably. But we'll see when we talk about Riemannian manifolds, this will be different. Okay. Um, so you've probably already seen the gradient, right? In like your multivariable calculus classes. Yeah. Okay. Two, if u is a function from Rn into Rn, then the divergence of u will be the trace of the derivative, and we'll call this div u. Finally, if u is a function from Rn into Rn, then the Laplacian of u, okay, uh, we might also write it like this, um, is the divergence of the gradient of u, which is nothing but the trace of the derivative of the gradient of u, which is nothing but the trace of the second derivative of u. Okay. Um, Sorry, this should be R into R. My bad. Do these operators make sense?
Sorry, what is trace again?
Um,
TR.
yeah, so the trace, so you can look at the trace in two different ways. One is the coordinate free way that we defined um in problem sheet one. So that's one way. The other way is to if you have a matrix, its trace is just the sum of the diagonal entries.
Mm.
Okay. Um, Turns out that in the case of one tensors, these are the exact same things. Because remember, matrices are one tensors, or we thought of matrices as one tensors. And so the way we defined the trace for tensors is like the more general version of the trace. Okay. Okay. So now we can like look at the integrals. So we have line integrals. So line integrals. They were like the integral over c of f dot dr. And then we wrote them using like um, these things. Um, and now in some sense, these integrals over here, they're one dimensional somehow, right? So we can ask ourselves, okay, is there a fundamental theorem of calculus type theorem that holds for this case? Yeah. So um, these look one dimensional. Again, don't fuss too hard about what dimensions means. Um, we'll define this more rigorously later on, but for now you can just think, how many variables do I need to you know specify my point um, on the surface. So for example, if you have a loop, it's one dimensional because I just need like one number can define where I am um, with the parameterization, for example. If I'm on a surface, then I need two numbers for my parameterization. If I'm in a volume, I need three numbers and so on. Okay. Um, just as an example, a circle has parameterization cosine t, sine t, right? So even though I specify two numbers, these numbers are specified by the parameter t. So this means that the circle is one dimensional. Sorry, one dimensional. Okay. That's just what I mean. Okay. So these look one dimensional. So is there a FTC type theorem? And the answer is yes. The answer is yes. So suppose I have f from R into Rn. Do I want R into Rn? No, I want R into R, sorry. Okay. Now, what I can do is I can make this a vector valued function by taking the gradient. So this is now a function from Rn and it gives me another vector in Rn. Okay. Do you agree with this? Okay. Um, so then the integral over c of the gradient of f is nothing but the function at the endpoint minus the function at the start point. All of this is wrapped in a very, very, very big asterisk. Okay. Um, Actually, sorry, it's not. It's not. I'm lying. Um, it's not. Um, okay. Does this theorem make sense? Does this look like the fundamental theorem of calculus? Okay. What I'm going to do is I'm going to define this object over here to be a zero-dimensional integral. Okay. Um, and that sort of makes sense because the endpoints are just points. So I don't need any numbers to, give you my point. I can just say I'm at this point or at this point. Since in some sense these are zero-dimensional objects. And the integral over a zero-dimensional object is just you give it some orientation. So you say this is the first point, this is the second point, and then you take the function at the second point and you subtract the function at the first point. Okay? That's what a zero-dimensional integral is. Does that make sense? Okay. So this is a one-dimensional integral. So we went down a dimension. Am I confusing? Uh, like, does what I'm saying make sense? So if you remember, even from like single variable calculus, the integral of f prime was nothing but f, right? So somehow you went down a dimension. So the derivative puts you down a dimension. Okay. So when we integrate the derivative of something, we integrate over a lower dimensional object and we integrate just the thing itself. Okay. We'll see that this is actually a general phenomenon that happens. Okay. Um, okay. Um, Let us now, how do I want to proceed from here? Okay, keep this idea in mind. Okay. Check the check the notes to see an example of this like being used. Okay. Okay. Now I can ask myself, okay, so we went down a dimension. Is it possible to come up a dimension? So instead of integrating in one dimension, can I integrate in two dimensions somehow? So say I have also one thing I want to notice is that if f is sorry, if c is a closed loop, um, then the integral over c of the derivative of something is zero. Okay, because the start point and the end point are the same. Okay. So the start point and the end point are the same, so the derivative must be zero. Um, and now we can ask ourselves the following question. If I have some vector valued function, okay, whose integral along a closed loop is zero, is it true that this vector valued function is the derivative of some scalar valued function? Okay. So look at the subtlety here. We saw that uh, the integral of the derivative of something is zero along a closed loop. And now we're asking the reverse question. I have something whose derivative is zero. Is it true that it must be the sorry, I have something whose integral is zero. is it true that it must be the derivative of something? Okay. Um, this is a very deep question that relates to the topology of our space. Um, and we will answer questions like this in a much more general setting using something called the Diram cohomology. Um, so cohomology is a way to measure holes in manifolds using integration. Um, or it's something like that, you know. Just think of the cohomology as telling you uh, if I have a hole of a certain dimension in my space. Okay. So we have okay, so did you understand like what the question was there? Like
Can you repeat it? Like again, I'm not really grasping this.
okay, so okay, we saw that if I have the derivative of a function, its integral on a closed loop is zero.
Yep.
Okay. Now the question is, if I have something whose integral is zero along a loop, must it be the derivative of something? So if integral along a closed C is a closed loop of f dr is zero, is f equal to the gradient of g? That's the question. Okay. Um,
Okay.
and it turns out that it depends on the topology of the space. Okay. Um, and then we'll discuss this we'll discuss this more using a technique from differential topology called the Diram cohomology. Don't worry about too much what cohomology means for now. All you need to know is that there's this mysterious thing called the cohomology of a space that we will use to, answer questions like this. And in some sense, we'll see that there's a relationship between the failure of this with the holes, with the number of holes in your space and the dimensions of your holes. Okay. Does that make sense?
Yep. Thank you
Okay.
so much.
Yeah. Okay, so now let's look at a general line integral. So suppose we have, the integral of so over a curve of p dx plus q dy. Remember, this is what the most general line integral looks like. If p and q are like c1, okay, then we can, instead of integrating over this loop, we can integrate over a boundary. Sorry, we can integrate over the surface it like, you know, um, encapsulates. So this will be the so it turns out that this integral is the same thing as the integral over a surface D of this object right here. Okay, where um, C equals the boundary of D. Here C is assumed to be simple, um, piecewise, piecewise smooth. Um, yeah, simple and piecewise smooth. Oh, and closed. Don't forget closed. Um, okay. So now it actually turns out that these two questions are very like closely related. Like these two questions are very closely related. We can now ask if when it is C the boundary of something? Okay. Is C the boundary of something? Um, and the the answer is actually a little shocking. Um, if you take C to be the closed circle, sorry, the a circle, okay, in R2, then of course C is the boundary of the disk, right? But what if I have R2 minus the origin? Is C the bound, is the circle a boundary of something now? And it turns out that the answer is no. Okay. We will prove this using something called the generalized Stokes' theorem, which I will introduce in just like in some time from now. Okay. Um, so yeah, one thing to notice is again, this looks very unnatural. Like, what is this object over here? Why are there partials? Why have they like swapped positions and stuff like that? So in some sense, we can already see from now that even in two dimensions, things start seeming very unnatural. You know, like up to this point, we were all good, right? Um, the dimensionality of our space didn't really make too much of a difference. But now we see this sort of formula can't really be generalized to three dimensions too easily. Because what would the proper generalization of this even be? Okay. We'll see later on that there's something called the differential operator that will actually take this and turn it into this in a natural way. And we'll see what natural means when we get there. Okay. This, by the way, is called Green's theorem. So this is called Green's theorem. And an application of Green's theorem is outlined in the problem sheet, in the third problem sheet. It has to do with the area, like the area of certain regions that are given by bounded, that are bounded by like simple closed curves. Okay, so now we've spent a lot of our time, just talking about two dimensions and stuff like that. Um, Three dimensions is a lot more interesting than two dimensions for sure. And in some sense, three dimensions is actually the most um, when it comes for integration at least of like integration of manifolds from what I know, three dimensions is one of the most interesting places to be. The reason why three dimensions is the most interesting is we'll define this later on, but the differential um, of a one-dimensional object is two-dimensional, right? Um, and it just so happens that three minus two is one. Okay. Um, somehow like three dimensions is special. Um, Again, this doesn't really make any sense right now. Um, but what we'll see is that three choose two is equal to three choose one. Um, so this will somehow be very important later on. But for right now, let's. So all I know is three dimensions are very, cool. Okay. So let's talk about so we've talked about lines in two dimensions or like curves in two dimensions. Curves in three dimensions basically have the exact same theory, other than you can't really have Green's theorem and stuff like that, but that's fine. Um, but you still have the fundamental theorem of line integrals. So let's talk about um, two-dimensional surfaces in three dimensions. Okay. two-dimensional surface. Oh no, let's call it A in R3. Okay. Um, what I mean by this is X, Y, Z in A if and only if um X equals like I don't know R um I don't want to write this. Um we can locally parameterize um A by R of ST equals X of ST, Y of ST, Z of ST. Um, have you seen this in 237, by the way, yet?
We did it. We did, yeah, yeah, we did this. Yes.
Yeah, you did, right? So I mean, it's the exact same thing. Uh,
Yeah.
so this is already the exam. This is like one of the first examples of a manifold, um, in the sense that we'll talk about it. Locally, it looks like the graph of a function. Okay. Um, but again, we'll look at manifolds and much more generality than um, just that. And this sort of assumes that you're embedded in some space. Okay. Um, then the surface area is given by so here S and T come from some domain D, um, and then this surface area is given by um, this weird looking object. Again, this seems extremely unnatural for now, but we will see that it's not that unnatural. Um, it looks unnatural because we're restricting ourselves to certain spaces. Um, Here, this is just the usual cross product. Have you seen the cross product?
No.
Okay. So the cross product. So let A, and let me not call this A. Let me say, I don't know. Let F and V be vectors or vector fields. Then F cross V. Um, the way F cross V is defined is that it's the vector that is perpendicular to both F and V, and it's normal to the plane spanned by F and V. And you choose it so that the right hand rule holds. Okay. Um, and a disc like the definition in coordinates though is you can write it as the formal determinant of like this. Okay. Um, Again, this looks extremely unnatural. I will keep emphasizing this fact. These look extremely unnatural. Okay. Also, do you see why? So you have something with two and then one. Do you see why two plus one equals three is now important? Because we have two things and we could get the perpendicular object. Right?
Oh, yeah, I see. Yeah.
This is one of the cases where like three being two plus one was, important. And what makes three dimensions special. Okay. Um, Another one we'll see is that three minus one is two. We will see that later on. Um, we'll define something called the Hodge star operator that will, generalize this notion of um, will it? There's nothing really like the cross product in higher dimensions, but there are definitely analogs to it. Okay. Um, so now that we have the surface area, if you remember how we did line integrals, we can also define the like the weighted integral, um, or the integral over the surface. So if f is a function from a into the extended reals, then the integral over a of f dA is nothing but the integral over d of f of like f composed with r times, this weird determinant, this weird derivative factor. Yeah. So this should be t to mu. Okay. One thing to notice, um, one thing of note is that um, you can check that this is equal to the determinant or the absolute value of the determinant of dr transpose dr. Okay. So in some sense, the determinant, as we see, keeps popping up, right? It popped up in the change of variable formula. It popped up when we talked about surface areas. It popped up even when we talked about, the length of a curve. So it also popped up when we talked about the what the volume of a certain rectangle in space was. So the determinant, or more generally, alternating k-tensors are very intimately tied to the idea of volumes. Okay. Um, so we will see when we define the integral over manifolds that the natural objects to integrate are these k-tensors that are alternating. The reason you need alternating is because the sign gives you a orientation, okay? That you can be oriented with or against, okay? Um, and the k-tensor just comes from the fact that this determinant is so intimately connected to the notion of volumes. Because remember what the determinant of a matrix is, right? It tells you how much does your volume scale when you do a linear transformation. Um, right? How much do volumes have to scale in order for this to, make sense? So when we talk about the derivative, we're doing sort of a linearization of the problem. We're looking very close and we're saying, okay, in this change of variables, in this change of coordinates, our areas have to scale by the derivative of the, change of variable. In order to encode this, we will integrate, k-tensors or alternating k-tensors. Um, we'll actually integrate something a little more general, but that's the idea. Okay. That's the motivation for why we even care. Like this is entirely the motivation for why I even introduced tensors to begin with. Okay. Tensors are very, very, very intimately connected to things like volume, especially linearized volume. By linearized, I just mean when you take a linear approximation of your problem. Okay. Um, but we run into the same issue, as line integrals. This sort of gets rid of orientation. So we would like to add back in the orientation. And to do this, we can define something called the normal vector. So the normal of a surface um, is defined by n hat. So it's a unit vector. Um, and it's just this volume element divided by its norm. Okay. Um, the way you want to think about this is um, uh, hmm, okay, I just realized I call these U and V, but this should actually be S and P. And the variables don't really matter too much, but let me just be consistent. Okay. Okay, so this actually brings up a good question. So the question is every surface orientable? As in, does there exist this normal vector for every surface? And the answer is no, right? I mean, one of the ways you can see that the answer is no is that this thing could be zero, right? If this thing is zero, you sort of blow up. But something more subtle actually happens as well. Um, imagine imagine a Mobius strip. Do you know what a Mobius strip is? Do you know what a Mobius band is? Mobius band, Mobius strip.
Oh yes, sorry, I forgot to open my mouth. Yeah.
Yeah. So if you look at a Mobius strip, if I'm pointing up and then I go around the strip once, I suddenly point down. Okay. And if I go again, I start pointing up again. So in some sense, this surface is not orientable, right? Something more subtle has happened. And we'll see that that's why we actually require the absolute values because, you know, things go to zero when they shouldn't, or when we don't want them to. And so the absolute value sort of, doesn't allow for a change of sign. Okay. So not all surfaces are orientable, and the surfaces that are orientable are called orientable. Orientable just means a choice of normal vector. So there are two vectors, right? There's one that points, say that I have a ball like this. There's one that points outward like this, and there's also one that points inward. If you can choose one um, smoothly, then you're orientable. So the Mobius band isn't orientable because you can't choose the up or down one differently. Okay. We'll define what orientable means more, you know, more rigorously when we talk about manifolds. Now, similarly, you can talk about like the flux over a surface or whatever. Um, and that's just defined. So if you have a vector field as a vector field, then the integral over the surface of f, you know, is defined to be the integral over s of f with this unit vector. Okay. If you want to see examples of this, you can check Griffiths, you can check Stewart. Um, there are a bunch of places where you can check. Okay. Now, let's ask ourselves this question again. Is there an FTC type like theorem for surface integrals? Right? And the answer is yes. Okay. Um, so for that first we have to define what it means to take the um, we need to do something. So before we like define this fully, and that's we need to define the curl. So curl of f. Okay. So if f is a function from R3 into R3, okay, the curl of f is defined to be, okay, the partial of f with respect to z. Wait, let me actually, okay. So it's going to be the partial of, yeah, with respect to z minus the partial of f with respect to y. Hmm, hold on, sorry. So f has three components. Is that it has fx, fy, and fz. So it's the partial of fx um, with respect to z minus the partial of fx with respect to y. Then you have the partial of f with respect, oh sorry, partial of fy with respect to um, x minus the partial of fy with respect to, so yeah, um, with respect to z, partial of fz. Actually, hold on. Let me not define it this way. This is kind of annoying. Um, you can look at it as the so I hat, j hat, k hat of partial x, partial y, partial z, fx, fy, fz. And if you write this out, what do you get? Let's see. So you get the partial of fz with respect to y minus the partial of um, y with respect to z. Then the partial of fx with respect to z minus the partial of z with respect to x. Partial of fy with respect to x minus the partial of fx with respect to y. Okay, so this looks again very, very, very unnatural. Um, there's a more natural way to define this, but that goes against what I want to talk about. So uh, we'll pretend like that doesn't exist. Um, and now this gives you a vector field, so you can integrate over a surface, right? And you can integrate over lines and stuff. So now the integral over a surface of the curl of f, okay, excuse me, is equal to the integral over the boundary of just f of, it's just the line integral of f. So we again have a theorem of the form integral of derivative equals integral over a like lower dimensional object of just the thing. Okay, I want to like contrast this with the fundamental theorem of uh, line integrals. You have the integral over a one-dimensional object of the derivative is the integral of the object in an n minus one dimensional thing. Here you have the integral of the curl of something is the integral of just the thing itself over a lower dimensional object. Okay, so this is a 2D integral. This is a 1D integral. Do you see why now I defined the endpoint, like the minus, like the subtraction of the endpoint thing as the zeroth integral? So now we have you have a formula that takes, a 2D integral to a 1D integral, a 2D integral, sorry, 1D integral to a 0D integral, 2D integral to a, 1D integral. And now we can ask ourselves, okay, can we keep going like this? Okay. Can we take the 3D integral of something and get a 2D integral of something? And the answer is yes. So so this is called Stokes' theorem. There's also something called the divergence theorem, where you have the integral over, a volume of the divergence of f. And this just equals the integral over the boundary of like the surface integral that we defined above. This is called divergence theorem. Okay, let's notice again, 3D integral becomes a 2D integral. And it has the same form. The integral of the derivative of something is equal to a lower dimensional integral of just the thing itself. So in some sense, all these things are actually the same thing. Okay. Um, and this is one of my favorite theorems in all of um, like manifold theory. and it's called the generalized Stokes' theorem. Okay? And it says that the integral over a manifold of this thing called d omega is the integral over the boundary of the manifold of omega. Okay. So it turns out that this thing is actually universal for orientable manifolds. That the integral of the derivative of something is nothing but the integral over the boundary of just the thing itself. Okay. Um, this this one theorem will be used extensively, and it's used everywhere. Okay, without um, a lot of the times without explicit mention. But we'll see that this is actually a very important theorem um, for us. I know today's meeting was very long. I didn't really expect that to be the case, but are there any questions? Like, are there any questions about anything we talked about today?
No.
Okay. I hope this at least gives you the motivation for um, the generalized Stokes' theorem and like why it's worth looking at integration on manifolds. Okay. Um, so yeah, I'll end the meeting.